In tropical water, an 18th-century warship could lose its speed to a living carpet and its hull to a mollusk that sailors called a worm. In tropical water, a wooden warship could be defeated without meeting an enemy. Weed and shellfish accumulated across its submerged planks until a swift frigate dragged a rough garden through the sea. Worse, shipworms bored into timber, leaving hidden tunnels beneath an intact surface. A captain could carry guns, powder, and train sailors across an ocean only to arrive in a vessel made slower and weaker by biology. The unlikely answer was to wrap the underwater hull in thousands of thin copper plates. Sailing performance depends on the part of a ship nobody aboard can see. A clean hull slips through water. A fouled hull wastes wind overcoming drag. That loss affects more than travel time. A warship must chase, escape, concentrate with a fleet, and maintain a blockade. Speed determines which battles can happen. Because growth continued while a vessel remained deployed, navies repeatedly had to bring ships into dock or careen them so crews could scrape and treat the bottom. Maintenance geography limited strategy. The other enemy, Teredo navalis, is called a shipworm but is actually a wood-boring bivalve mollusk. It enters timber small and excavates along the grain while leaving little evidence outside. Warm waters made the danger especially severe for vessels operating far from northern dockyards. Navies tried tar, hair, paper, extra wooden sheathing, and metals. Lead could protect wood but created practical difficulties. Copper promised both a barrier against boring organisms and a surface hostile to much fouling. The Royal Navy conducted its famous full-hull trial on the 32-gun frigate HMS Alarm in 1761. Copper sheets were fastened below the waterline. The trial confirmed important benefits: marine growth was reduced and shipworm damage prevented. Royal Museums Greenwich explains the mature purpose plainly: copper stopped weed buildup that damaged sailing qualities and protected underwater planking from Teredo, reducing expensive dock repair. But Alarm also revealed that a useful idea could threaten the ship in a different way. Copper and iron in seawater create an electrochemical system. The copper sheathing accelerated corrosion of iron fastenings in contact with it. 18th-century shipwrights did not use modern language about galvanic cells, but inspection made the pattern alarming: bolts essential to the hull were deteriorating. The Navy removed copper from Alarm and paused broad adoption while it searched for ways to isolate metals or substitute copper alloy fastenings. The skin that protected timber could consume the skeleton holding it together. This near failure is central. Technologies rarely arrive as clean substitutions. Copper was not simply better than wood coatings, it interacted with every nail, bolt, layer, dockyard practice, supplier, and budget around it. A thin sheet altered the material environment of the whole hull. Had officials focused only on the clean copper and ignored hidden iron, ships might have appeared healthier while losing structural security. Successful adoption required treating the vessel as a system. Further trials followed. Naval Historical Research describes a 1769 experiment using copper alloy bolts below the waterline. Shipwrights also placed protective material between copper and iron and improved fastening practice. By the late 1770s, strategic pressure made the reward irresistible. Britain was fighting the American War of Independence, soon facing France and Spain across a wide maritime theater. In 1779, the Admiralty moved toward coppering the fleet, and scholarship describes the decision as a fleet-wide program. The timing mattered. A ship with a cleaner bottom could retain speed longer between dockyard visits. It could spend more time on station and less time being hauled out. A blockade is not one dramatic battle, it is repeated presence. The operational value of copper therefore multiplied over months. It increased the useful reach of existing hulls without adding a mast or gun. A navy purchased persistence by covering the least glamorous surface of its ships. Coppering was expensive. A ship required large quantities of rolled metal and skilled labor to fit overlapping plates around a curved hull. Britain's industrial supply helped make fleet adoption possible. The expanding Perry's mountain mines on Anglesey became a major source of copper, while rolling mills transformed ore into uniform sheet. Naval demand in turn stimulated mining, refining, rolling, and standardized marking. The underwater skin connected imperial strategy to landscapes and factories far from the sea. It also shifted the economics of maintenance. Copper cost money at fitting, but fouling cost speed continuously and shipworm cost timber, dock space, and labor. The correct comparison was not copper versus nothing. It was copper versus repeated cleaning, replacement planking, lost availability, and strategic delay. This lifecycle reasoning is now routine in engineering procurement, yet it is easy to miss when looking at a shiny new sheet. The Navy was buying fewer future interruptions. The tactical effect must not be exaggerated into a single cause explanation for British victories. Gunnery, command, seamanship, logistics, weather, intelligence, and enemy decisions remained decisive. Historians debate how much particular operations owed to copper. But the general capability is secure, reduced fouling preserved sailing qualities, and the Royal Navy's early, large-scale adoption gave it an operational advantage until rivals caught up. Copper did not win wars alone. It made more ships more available to fight them. The phrase copper-bottomed eventually escaped the dockyard. Royal Museums Greenwich links it to ships sheathed in copper or brass and explains that metal stopped barnacles attaching and slowing them. In ordinary English, a copper-bottomed plan or investment came to mean thoroughly sound and dependable. The metaphor is revealing because the original technology was dependable only after a dangerous flaw was addressed. Its reputation for reliability was earned through inspection, failure, redesign, and system-wide adoption. Copper sheathing also created a visible signature. When a vessel heeled, observers might glimpse the warm metallic band below the black hull. Over time, the surface weathered and reacted. Yet most of the strategic work occurred underwater and out of sight. This is a recurring pattern in infrastructure. The components most responsible for dependable service are often the ones passengers, citizens, and even commanders rarely see: insulation, seals, drainage, standards, coatings, and maintenance schedules. Consider a counterfactual fleet without effective sheathing. Ships deployed to the Caribbean or other warm stations would still operate, but they would foul sooner, require more maintenance access, and risk more worm damage. Admirals would need larger margins because a nominal fleet list would conceal vessels unavailable in dock. Chases could fail as relative speed changed. Distant bases would become even more important. Copper did not abolish these constraints, but it loosened them enough to change what commanders could reliably ask ships to do. The innovation also shows why military power is often logistical before it is dramatic. Paintings celebrate broadsides and boarding actions. Copper sheets rarely appear in heroic compositions because they sit below the water. But battle begins with arrival. A ship that cannot maintain speed cannot force action on favorable terms. A vessel awaiting repair cannot blockade anything. By extending intervals of effective service, sheathing converted mined metal and dockyard labor into days at sea. There is an environmental irony. Copper worked because its surface was biologically unfriendly. It changed the miniature ecosystem trying to settle on a hull. Modern anti-fouling technologies still negotiate the same problem, preventing growth without imposing unacceptable environmental costs. Materials have changed, regulations have changed, and steel hulls replaced wooden fleets, but ship operators still pay heavily for drag. The 18th-century copper experiment belongs to the continuing history of energy efficiency as much as naval warfare. The galvanic corrosion episode offers the most useful modern lesson. An improvement can solve the visible problem and intensify a hidden one at the interface between materials. Engineers now deliberately use sacrificial anodes and isolation to manage electrochemical corrosion. The underlying rule is the same: one alarm exposed, seawater connects metals electrically, and the less noble metal may be consumed. A ship's copper skin became an accidental chemistry demonstration at full scale. Look at a museum model of a sailing warship and attention rises naturally to carved sterns, gun decks, and rigging. Turn the model over. The plain lower surface carried a strategic technology. Thin sheets prevented animals and plants from stealing speed, while revised fastenings prevented the cure from eating the ship. Once those details worked together, wooden vessels could remain effective farther from repair. The plates demanded standardized work. Copper had to be rolled, transported, cut, overlapped, pierced, and fastened around complex curves. Dockyards needed schedules and supplies large enough for a fleet. One beautifully coppered frigate was an experiment, hundreds of maintained hulls were a capability. Strategic advantage depended on mundane manufacturing consistency. Scale changed relations between navy and industry. Government orders encouraged output while inspectors worried about quality. A plate too thin might save a contractor money but shorten service. A fastening selected without regard to electrochemistry might compromise expensive timber. Procurement and material control became as relevant to sea power as an admiral's signals. The copper skin was also an administrative system. Other navies observed and adopted sheathing, narrowing Britain's early advantage. That is typical of practical innovation. Success teaches competitors. The lasting shift is broader than the first advantage. Once ships can retain speed longer, plans assume that performance and the old maintenance burden becomes unacceptable. The innovation moves from novelty to infrastructure. Fleet adoption also changed the meaning of readiness reports. A ship listed as commissioned was not necessarily a ship able to chase at design speed. Fouling created a slowly growing gap between paper strength and practical strength. Copper narrowed that gap, making administrative counts better predictors of operational capability. This mattered to planners deciding how many vessels could be spared for distant stations. The innovation reached merchant shipping as costs fell and methods spread. Traders valued speed, longer intervals between dockings, and protection on warm water routes for commercial reasons rather than battle. The same sheet could translate into faster passages and fewer repairs. Naval experimentation thus joined a wider transformation of ocean transport, though adoption varied with route, hull, capital, and access to suitable yards. Seen from shore, coppering was easy to underestimate because it did not change the ship's familiar silhouette. That invisibility helped turn it into infrastructure. Sailors adjusted expectations, dockyards built routines, suppliers filled contracts, and commanders planned around cleaner hulls. Once embedded, the innovation stopped appearing as an invention and became simply how a serious vessel should be maintained. Dependability accumulated through thousands of hidden, repeatable acts of maintenance and inspection. That is the retellable connection. Britain's age of sail reach depended partly on wrapping oak ships in copper, and the experiment helped reveal the danger now called galvanic corrosion. The same metal skin that made warships faster first attacked their iron bolts. Only by solving that hidden reaction did copper-bottomed become a synonym for reliable. A naval advantage, an everyday phrase, and a basic engineering warning all meet on the unseen underside of a wooden naval hull.